All right, a very good evening, everyone. So, we are into the eighth lecture of social media analytics. Okay, so let me give a quick recap of what we have covered in our last lecture. Okay, so in our last lecture, we studied about homophily. Homophily is a property by which, like in social networks, people tend to connect with each other. Okay, so for example, whenever you are choosing the subjects, okay, you tend to choose the subjects which your friends have chosen. And also, you can take the example of moving into a new society. So, whenever you move into the new society or you are trying to search for the locality, you try to shift in the locality where there are more people belonging to your community, to your religion, and so on. Okay, so that is called as a property of homophily. So because of homophily, because the homophily exists in social networks, so there emerges the communities. Okay, so we have studied that communities are nothing but subset of nodes in the network that are more connected within themselves than the rest of the network. We have also studied that communities and community identification in the social network have various applications. Okay, so starting from recommendation system to fake news detection to information diffusion. So there are a lot of applications that comes from community, identifying community, and uh, using the communities in social network. So that's why, like, identifying community is one of the very important topic in social network analysis. Then next, in the last lecture, we have discussed that communities can be of various types. There can be disjoint communities. So in the disjoint community, each and every node will belong to only one community. Okay, so there cannot be a node that belongs to more than one community. This is called as disjoint community. Then the next type of community was overlapping communities. So this is a more natural form of community structure because, like, in real world, we belong to different communities. Okay, we do not belong to just one type of community. We belong to different type of community, and we belong to different overlapping communities. Okay, so there can be community related to our work. There can be communities related to our relatives, friends, and so on. Okay, and then we have also studied that there is third type of communities that is called as hierarchical communities. Okay, so the algorithms that are applied to identify disjoint communities can also identify hierarchical communities. Okay, so in today's lecture, we will be seeing how the algorithms that are used to calculate the disjoint communities can also be used to calculate the hierarchical communities. After this, we also covered the topic of local communities. Communities can also be called as ego networks. Okay, so what is ego network? When I am considering me as a node, and then I'm considering my own connections and the connections of my friends and so on. Okay, so when you are concentrating on one single node and you are trying to look into its locality or into its neighbors and then neighbors of neighbors and so on. Okay, so when you are exploring this type of structure in the network, that is called as local community. Okay, so these were the different community types that we have covered. Then we started with studying the algorithms to identify the communities. So we have seen various different algorithms to identify the communities. First, we started with node-centric community detection, where we use the properties of nodes in order to identify the communities. So we have covered a lot of algorithms in these sections. These were K-cliques, K-clans, K-clubs, K-plex, and so on. Okay, and then like after using the node properties, we studied that we can also use the edge properties in order to identify the communities in the network. Okay, so you try to identify the cut. Okay, so minimum number of edges that should be removed in order to get the communities. So that is called as cut. So then we saw what is a ratio cut, what is normalized cut, and how these two help to identify good communities. Okay. So then next we covered another very popular algorithm that is based on edge betweenness. Okay, so it calculate the edge betweenness of all the edges and then sort the edges and then try to delete the edges one by one for those edges, like those have maximum edge betweenness. Like the edges will have maximum edge betweenness if they are joining two or more groups. Okay, so in this algorithm we delete the edges based on edge betweenness. Okay, so we have studied that all these algorithms were very expensive to compute. So next we studied that there can be one measure that is called as modularity. So modularity has again, gain a lot of attention in the literature of community detection. So this is one of the most popular algorithm that is used today to calculate the communities in large networks. So in the last class, I have also shown you the project that I was working on where I was handling a lot of communities, right? So I've shown you that I have developed a visualization for very large networks where we identify the communities. So whenever we have a very large networks, generally most of the algorithms, they are very expensive to compute. So in those cases, we use modularity based algorithms. Okay. So today we are going to study what is modularity and what are the different algorithms that are based on modularity. Okay, so with that quick recap, let's start with our today's lecture. And in today's lecture, we will start with discussing the modularity. Okay, so now what is modularity? So modularity is a node-centric method, okay, and then it consider the word as module, okay. It consider the network, the modules in the networks, okay. So now, what is the idea or ideology behind modularity? So in modularity, we try to identify or we try to compare the actual number of edges in the community to the expected number of edges in the community. Okay, so these two terms are very, very important when we are trying to understand the notion of modularity. The actual number of edges that are there in the communities and the expected number of edges in the communities. Okay, so now let us elaborate what is expected number of edges in the community. Okay, so now consider a random graph. Okay, so what is random graph? So anybody do you want to answer this question? What is random graph? And what is the difference between social networks or social network and a random network? What do you think is a random network? Okay.
And
For
random network
Mhm.
is it's a concept actually where we start from a node and
Mhm.
we take some probability distribution, and with that probability distribution we keep on moving to other nodes for some number of nodes, and in this
Mhm.
way whatever graph which is created is a random graph. And generally random graphs, if we create, then the distribution will be kind of uniform, but actual social network graph obeys the power laws. Well, this is
Correct.
my.
Yeah, the answer is almost correct. Okay. So what is random graph? So random graph is, suppose you have n nodes. Okay. So for these n nodes, now you consider each pair of node and you toss a coin. And then based on whether it's head or tail, you decide that whether you want to add an edge in this network or not. So you see that in the random graph, there is no concept of homophily. Okay. And there is no preferential attachment in the nodes. So because there is no homophily in these random networks, so there are no communities in this network. Okay. So generally the random graphs, they won't have the communities in it. Okay, so now we are going to compare the actual number of edges in our network to the number of edges in the random graph. Okay, so now for our network, we will generate an equivalent random network. And in that random network, we will try to compare the number of edges that are there in that community versus the community that is there in our network. Okay, so now this might sound confusing at this point of time. Okay, so let me explain you with the help of an example. Okay, so suppose, let me consider an example of a network. So suppose I have, sorry. Okay, so let us suppose that we have this network. Okay, this is 1, 2, 3, 4, and 5. Okay, and I want to generate an equivalent random network for this graph. Okay, so when we are generating the random network that is equivalent to this particular graph G, okay, so first of all, we should try to retain few properties in the network. Okay, so what is that property that we would like to retain in the random network? That is the degree distribution. So we try to preserve the degree distribution in the random graph. So let us suppose the random graph is GR. So the random graph is GR. GR should have same degree distribution as G. Okay, so now from G, we will try to generate a GR, and in GR, the degree distribution should be same as that of G. Okay, so now next, in order to define this graph, in order to generate this graph, we define something called as configuration model or null model. Okay, so we define configuration model or null model. Okay, so now for now, you can understand this that we are going to generate a random network that is equivalent to G by using null model. Now, next I will be explaining what is null model. Okay, so up till now we have studied that we are trying to preserve the degree distribution, and using the null model, we are going to generate a random graph. Okay, so now what is null model? In null model, you will divide each edge into two half edges. Okay, so we have this edge, for example. So each of the edge will be divided into two halves. Okay, so first of all, let us consider all the vertices. We have vertex 1, 2, 3, 4, and 5. Okay, so now, first of all, we are trying to preserve the degree distribution. In order to preserve the degree distribution, what we will do is we will divide one edge into two half edges. So how we will divide into half edges? For example, here we have degree 2. So this edge I have divided into 2 edge. So again here I have degree 2, I have divided this edge into 2 edge. Here I have degree 1, so I have divided it into 1 edge. And here I have degree 3, so I have divided into 3 half edges. Then here we have degree 2, so I have divided it into 2 half edges. Okay, so by doing this, you can see that degree of each node is preserved. Okay, so now what is the first step? The first step in the null model is to divide each edge into two parts called as half edges. Now, next step is choose one of the half edge. So you can choose one of the half edge, and from the remaining half edges, you can randomly connect it to any of the half edge. Okay. So for example, I can connect this edge to maybe like this. Let me consider this edge. So now for this edge, I have all these options. Okay. So I have all these options. So let me join this to this edge. Okay, so this is the first edge I have. Then let me consider this next edge. So this edge, maybe I will join to this edge. Okay, so now I'll consider this half edge. So this half edge, I'll look into like what all remaining edges do we have. So maybe I'll join this to this edge. Then I have this edge. So this edge, maybe I'll join to this edge. And then I have this edge, so this edge will be joined to this edge. Okay, so this is one of the random network that is generated by using null model. Okay, so what we have done is we chose one half edge and randomly chose remaining half edges to connect. Okay, so now this is how we generate the random networks. Okay, so now here there is another point that you should consider, that for a single network, there can be many different random networks. Okay, so you can try it out on your own. So this is one of the random network that I have created, but in reality, there can be more than one random network. So there can be many random networks for one network, because we also allow parallel edges here. So we also allow parallel edges and loops. So there can be many different random networks for a single network. Okay. So now what is the next step? Okay, so what we are trying to do when we are trying to identify modularity, suppose this was a community here. Okay, so suppose this was a community in the original network. Okay, so let us suppose that we already have communities. Okay, so in the original network that we considered, let us suppose that 2, 3, 4, and 5, these nodes belong to one community. Okay, so now we will try to identify the number of edges in the graph that we are considering and the number of edges in the random graph. Okay, but we also know that there can be many random graphs. So what we will do is we will try to identify the expected number of edges in the random graph. Okay, so now what you need to do is you need to compare the number of edges in original graph and in random graph. Okay, so what you need to do in order to find the modularity. So this is the notion behind modularity. What you will do is you will compare the number of edges in original graph and expected number of edges in random graph. Why we are using this word expected? Because because for a single graph, there will be many random graphs. So we need to find the average of the edges that are there. Okay, so that is why we are using this word expected. So you need to compare the number of edges in original graph to the expected number of edges in the random graph. Okay, so there will be some difference. Okay, so now I want you to identify if the difference is more. Okay, so if the difference is more between the original network and the random network, so whether it is a good community or not. Can anyone answer? What will be the quality of the community if the difference between the actual community edges and the difference between the random network edges is more? Will the quality be good, bad? What do you think?
It will not be a good quality.
Okay. Anyone else want to try? Okay. So when we started this lecture, okay, so we have discussed कि random network क्या होता है, okay, and we have discussed that random network में there are no communities, okay. So now if both these values are almost same, अगर हम compare कर रहे हैं the number of edges in our graph to the number of edges in like number of edges in the random graph community. So if there's no difference, so that means there is no community in our given graph. Okay, so the quality of the communities will be better if the difference will be more. Okay, so more the difference, better will be the quality of communities. Okay, is this point clear to everyone? Any doubt up till now? More the difference, better will be the quality of community. Is this point clear to everyone? Anyone have any question up till now? Okay.
Ma'am, how we are calculating the difference? Like, what difference we are measuring here?
Okay, so that mathematical calculation will be more clear when I will be explaining you further. अब अभी तक मतलब ये जो idea है, is the idea clear? या idea में
Yeah,
कुछ doubt?
yeah, that's
Okay, so idea is clear कि मतलब random में there is no communities. Okay, so random if this is the community. Okay, so this is the community. We are trying to calculate the number of connections between these nodes that fall into one community. तो अगर random में भी उतने ही edges हैं and हमारे original graph में भी उतने ही edges हैं, then we will say कि इस graph में ये community ही नहीं है, because random में we know whatever we have that is not a community, right? So अगर इनमें कोई difference नहीं है, ये same है, same number of edges है, then we will say कि like this is not a community. But if the difference is more, okay, so if the difference is more, then we can say that okay, this graph has a community, and that is a like more the difference, better is the quality of the community. Okay, so now next we will try to mathematically define the modularity formula. Okay,
Ma'am,
so
may
this,
I ask one question?
yes.
Ma'am, इसमें that point number 1 where you have written that we have to divide each edge into two parts called as half edges. तो इसमें like when you were dividing तो आप 5 को you have divided into 3 parts, so that is allowed, or even if we have got 3 edges तो भी हमको 2 ही रखने हैं?
देखो, in this हम क्या कर रहे थे, we were trying to preserve the degree distribution.
Yes,
ठीक है,
ma'am.
तो डिग्री सेम रखनी है, हर नोड की डिग्री सेम होनी चाहिए.
Like because I got confused because divide each edge in 2 parts, so
हाँ,
मतलब 3 कैसे करेंगे?
ओके, सो लाइक ये एक फुल एज है, राइट? दिस इज अ फुल
Yes,
एज. तो हमने क्या किया, व्हेन वी आर ट्राइंग टू कंप्यूट द रैंडम ग्राफ, तो हमने ओरिजिनली ऐसे कंसीडर किया था हाफ एज.
yes, ma'am.
Sorry, this was a full edge. This was a full edge. Okay. So what we have done is we have considered half edge. Okay.
Yes, ma'am.
So we have considered half edge. Half edge का मतलब half यहाँ पे आ गई, half यहाँ पे आ गई.
Okay, ma'am.
Okay. So अगर हम ऐसे half edge में divide करेंगे तो degree of each node will be preserved. Now considering one particular edge, you have all the other different options you can join anywhere.
Okay, ma'am. Understood.
Yeah. Okay. So now let's move on to the mathematical calculation of the formula. So I will be mathematically explain you what is the formula of modularity, and I hope the notion behind the modularity is clear to you. So this was one of the method जिससे आप communities तो calculate कर ही सकते हो, but you can also identify what is the quality of the community, whether the communities are good or bad. Using this particular formula, you can quantify the quality of the communities. Okay, so we know that there can be more than one random graphs for a given graph. Okay, so we know there can be more than one random graphs. Okay, therefore, we take the expected number of edges in random graphs. Therefore, we take expected number of edges in random graphs. Okay, so now let us suppose we have a graph GVE where V is the edges and E are the edges. Okay, so V is the vertices and E is the edges. Okay, so now we are trying to compute GRVE where number of vertices and edges will be same. Okay, so first of all, the total number of half edges. So what will be the total number of half edges?
Twice the edge.
Right. So total number of half edges will be equal to twice. Let us consider that m is the number of edges. Okay, so if m is the number of edges, then the total number of half edges will be 2m. I can also write it as summation of the degrees of all the nodes. Okay, where I belong to all the vertices. Okay, so is this notion clear? So total number of half edges will be equal to 2m, or the summation of all the degrees of all the or summation of degree of all the nodes. Okay, so now suppose let us consider 2 points I and j. So I has some degree and j has some degree. Okay, and these are the half edges of I and j. Now let us consider node I has degree di. Okay, so node I will have degree 1, 2, 3 up till di. Now, so now what is the probability that there will be that suppose this is an edge. So this is an edge and it will be connected to one of the edges here, one of the half edges here. So what is the probability that one of the edge here, suppose that has an index B. Okay, so let me consider this edge. What is the probability that it will be connected to one of the edge here of the node G? Anyone can answer?
3 ways.
Okay, so let us suppose the degree of node J is dj. Now anyone can answer? What is the
J.
probability? What J na?
1 upon di dj.
1 upon J.
So it will be dj divided by 2m. So 2m was the total number of edges. Okay, so 2m was the total number of half edges. So dj, so if this edge is connected to one of the edge here, okay, one of the edge here. So how many option it has? It has dj options. right? Is this clear? So the the expectation, okay, so the expectation that this particular edge will be connected to one of the edge here will be dj by 2m. Is it clear?
Ma'am, can you explain what is DJ again, ma'am? Actually, I missed that. 2M is clear, ma'am. DJ.
Okay. Okay. So suppose there are these two nodes. This is I and this is J. Okay. So we are considering one of the half edge here. Let us name it as B. Okay. So although there were many edges, but we are considering this particular half edge. Okay. So now we are trying to compute ki what is the probability this is connected to one of the edge here. And the degree of node J was DJ. Okay. So there were DJ half edges here. Okay, so now what is the probability that this will be connected to one of the half edge at J? So it will be dj divided by 2m. Why? Because this particular half edge, how many options it has? It has dj options, right? Because dj was the degree or dj was the number of half edges. So now is it clear?
Yes, ma'am. Yes, ma'am. Yeah.
Okay, okay.
अरे
So
क्या
now,
बात है?
let us try to calculate. Gaurav, can you put your mic on mute, please? Yeah, thank you.
Oh, sorry.
Okay, so now next we are trying to compute total number of full edges between I and J. Okay, so initially we have calculated considering one edge, whether it is connected to one of the edge at DJ or not. Okay, so now let us calculate the total expected number of edges between between I and J. Okay, so between I and J, if I am trying to calculate this, then that means for each and every edge here, I have DJ options. So this will be equivalent to DI DJ by 2M. So is this clear, this formula? The total number of full edges, total number of expected full edges between I and J. It will be DI into DJ by 2M. Is it clear? Up till now, any doubt, anyone? How this formula came? It is clear to everyone?
Yes,
And
ma'am.
is this probability or total absolute number of?
Expected number of edges we are calculating.
Okay.
So now let's calculate the modularity. So modularity is represented by Q. Okay, so the formula for this is 1 by 2m. Okay, so now first of all, we are going to consider I and J, where I and J belong to all pair of vertices. Okay, so we are considering all pair of vertices. Okay, so this is represent all pair of vertices. Okay, and then we have AIJ. Okay, so AIJ is the adjacency matrix. AIJ is the adjacency matrix, and this will tell you the actual number of edges. Okay, actual number of edges in the network. So whether like two nodes are connected in the edge or not. So this will give you actual number of edges minus dij by 2m. Okay, so this is the expected number of edges between I and J. Okay, so what we are trying to calculate here, we are trying to calculate the actual number of edges minus the expected number of edges. Is it clear to everyone? This formula up till now? Okay, so now in this formula, yes.
You said Dij, right? Summation of Dij.
Hmm.
That's the distance, I mean, the number of edges between I and J.
Yes, expected number of edges between I and J.
And whereas Di is the total number of edges, right?
Di is the degree at node I.
Okay, in degree, out degree, okay, degree at
Yes.
number of, okay.
Yes,
This
or
is,
the
this
number of
is,
half edges at I.
okay, okay.
Yeah. So, so in initially, what I told you, the notion behind modularity is that you will calculate you will subtract the actual number of edges from the expected number of edges. So this is the formula. So now in this formula, we also have to consider that whether two edges, they belong to same community or not. Okay. So this formula is only applicable when two nodes, they belong to same community. Okay. So only then we are going to calculate. You have seen here that we have only considered these nodes. Okay, these belonged to single community. Okay, and then we tried in this community, we tried to identify the difference between the number of edges in the original graph and in the random graph. Okay, so now we will try to see that whether I and J belong to same community or not. For that, we will use one indicator that is called as delta Ci and Cj. Okay, so what is delta Ci Cj? Okay, so delta CICJ, it is an indicator that tells that whether I and J belong to same community or not. Indicator that tells whether I and J belongs to same community or not. Now, the value of Ci and Cj will be equal to 1 if both I and J belong to same community. Okay, so if both these belong to same community, then the value will be 1, otherwise the value will be 0. Okay, so this is the formula for modularity. Okay, so now let's move back to our slides. Okay, so now I will read these points and I hope like it will be very clear to you with the explanation, whatever I have given till now. Okay. So what is modularity? It is a community-centric method discussed so far are not very useful. Okay, whatever methods we use till now were not very useful for large networks. For large networks, we need some new method that could be applicable and that should be more efficient. Okay, so there comes the notion of modularity. What is the modularity? Modularity is basically, it is based on the principle of comparison. We need to compare the actual number of edges in the subgraph and its expected number of edges. Okay, and in order to calculate the expected number of edges, we use the null model. Okay, so in order to calculate the expected number of edges, you need to use the null model. I hope these terms are very clear to you. Null model, expected number of edges. Now, what is null model? In null model, each vertex is randomly connected to another vertex irrespective of the community structure. However, some of the structural properties are preserved, and that property is the degree distribution. So I've shown you that how null models are created, how degree is preserved, and how do you calculate the expected number of edges. Okay, and this is the formula. The formula I have clearly explained you like what each and every variable it represents. So again, Aij is the adjacency matrix, so it will give you the actual number of edges in the graph, and Ki into Kj will give you the expected number of edges between I and J, between node I and J. And then we are calculating this indicator. So this indicator will be 1 if both I and J belong to same community. Otherwise, it will be a 0. Okay. So yeah, so now you can calculate the modularities, and the modularities values will vary between 0 and 1. Now, The value of the modularity, if it is very close to zero, so then we can assume that there is no community structure. Okay. And if the value is between 0.3 to 0.5, then it is considered that it has moderate structure. And if the modularity value is greater than 0.5, then we say that the network has strong communities. Okay, so this was the formula, and now like for the questions that we are going to solve, we are going to use this particular formula. Okay, so this is a slight variation of the modularity formula for easy calculations for like small networks that we are going to solve with pen and paper. So we are going to use this particular formula. So in this formula, the number of edges inside the community, LC represent the number of edges inside the community. Okay, so in the example that we have seen. Okay, so if I consider this particular community, the community that I have circled in view, what will be the LC value? LC value will be 1, 2, 3, and 4. Okay, so this is the number of edges that are there in the community. Is it clear? What is LC? LC is
Yes,
the
ma'am, it is clear.
number. Yeah. Okay. So then we have M, M is the number of edges. Okay. And then we have DC. This is the sum of the degree of nodes in the community C. So whatever community we are considering, so DC is the sum of all the degrees in that community. Then that divided by 2m square. Okay, so using this formula, you have to calculate the modularity. So how you will calculate modularity? You will calculate the modularity for each and every community. Okay, so suppose I had a graph. Okay, so suppose I have some graph like this. And there were like different communities. So for each and every community, I have to calculate this particular function. Okay, so for each and every community, I will calculate, and then summation on all those different modularity value will give me the total modularity value. Okay, so now with that, let's solve our first question. Okay, I'll give you the formula here. Okay. Okay, so I want you to use this formula and calculate the modularity value for this particular question. So I'll give you 2 minutes. So use this formula and calculate the modularity value. So this question is pretty easy because like you only have to, this is direct calculation. You only have to input the values and get the answer. So please let me know if anyone is done.
On 0.24.
Correct. Okay, so you have to straight away input the values in this formula and get the answer. Okay, so now suppose you have these two communities. So now how you will calculate?
Summation of both, ma'am. I mean,
Yes.
we'll have to calculate individually and then summation.
Individually, yeah, you have to individually calculate the modularity value of these two, and you have to do the summation, and that will give the modularity value of the entire network. Okay, so now let's take a break of 10 minutes. Okay, and I would expect that after the break, maybe you should have answer to this question as well. So what is the answer to this question? So maybe I'll paste the formula here. Okay. So yeah. So then we will meet after 10 minutes and we will discuss the answer to this question. And also we will move on to our discussion of the algorithms, the community detection algorithms that are based on modularity maximization. Okay. All right. So welcome everyone. Okay, so this was the question that we were discussing before going to break. Anybody has an answer to this question?
Yes, ma'am. It's a 0.335, right?
Okay, let's check. So this is the answer. Okay, so I will share these slides. You can check the calculations that how.
Ma'am, can you share the screen, madam? I think it's not shared.
Oh, okay. Sorry. Okay, so yeah, this is the answer to the question. Yeah. So this was all about modularity and calculating the modularity in the network. Okay. So now, like the scientists, they thought that why can we use this particular measure in order to calculate the communities in the network? Okay. So initially, this measure was developed to, quantify the quality of the communities. Okay, so when you want to identify like whether this is a dense community or it's a sparse community, so what is the quality of the community in order to identify that this particular measure was developed, that is modularity. Okay, so now the scientists they started thinking that whether can we use this particular measure in order to identify the communities. Okay, so now they try to optimize the modularity in the network. Okay, so they try to maximize the modularity. So there are different algorithms that are based on maximizing the modularity in the network and identifying the communities by maximizing the modularity value. Okay, so there are the two algorithms, fast greedy algorithm and Lowain method. So Lowain is again a very popular method in order to identify the communities. So let's discuss these methods now. Okay, so let me discuss it on the pad. Okay, so like first of all, we have this method called as fast greedy algorithm. Okay, so how does fast greedy algorithm work? Suppose this was my input graph. Okay, so initially what you will do is you will consider all the vertices and all the vertices are divided into different communities. Okay, so each community, each node is assigned to a different community. So you can see that here all the nodes are colored differently. So that means that all the nodes they belong to different communities. Okay, so now initially what it will do, it will start with some random node. Okay, it will start with some random node. For example, we started with node 1. Okay, so now it will try to see with which all node this particular node is connected. So 1 is connected with 2, it is connected with 3, and it is connected with 4. So one by one, it will try to assign this particular node to the same community as 1 and identify the modularity. Okay, so what it will do? So firstly, it will assign these both to one community. It will add this edge and it will identify the modularity for this particular network. Okay, so now next, suppose the modularity for this is 0.7. Okay, so now it will consider the next node. So one by one, it will, so now for next node, it will not consider this edge. Okay, so what it will do is it will consider this particular edge. It will assign 1 and 3 to the same community. Then it will identify the Q value. For example, that maybe that Q value is 0.65. Okay, and so on. So it will try to compute with all the other nodes that are connected. Okay, so now after identifying these, it will try to see that where the modularity value was maximum. So wherever the modularity value was maximum, it will freeze that node into one community. So for example, currently, let us freeze this and let us assume that this modularity value was maximum. Okay, and because this was maximum, both this node and this node, they belong to one community. Okay, so now in the next step, what it will do is it will now try to consider all the connections from this and all the connections from this node. Okay, and for each connection, it will try to put that particular node into the same community as this community, and it will try to identify the modularity value. Okay, so since this is greedy method, so you can that in greedy methods this happens that you usually try to freeze the first maximum value. Okay, so now again in this step it will try to maximize it will try to identify the modularity by assigning one by one node to this particular community that was freezed in the previous step. Okay, so for example, it will try to assign this node to this community, then maybe this node to this community, then maybe this node to this community, and so on. Okay, so now suppose that if I assign like Q value here was maybe zero point 0.8, here was zero point 0.7, here was zero point 0.6, and so on. Okay, so because modularity value is maximum here. Okay, so now it will assign this particular node to one community. Okay, so now all these three nodes, they belong to one community, and the remaining nodes, they belong to single separate communities. Okay, so now comes the third step. Okay, so in this way, it will continue till the time Q value at a step is starts decreasing. Okay, so suppose now I move to next step. Okay, so in the next step, when I try to again assign another node to this community. Okay, so this is the community. So now I'm trying to assign one more node to this community, and maybe the Q value, it is now 0.75. Okay, so at this third step, maybe the maximum Q value is 0.75. Okay, so if the maximum Q value is 0.75, we will stop there. Okay, so in each and every step, when you are assigning a node to the particular community, the Q value or the modularity value should increase. If it is not increasing, we'll stop. Okay, so we will stop at this point, and then again we will consider another seed point. Okay, so we will consider another seed point, and then again we will try to put the other nodes to the community that that particular seed belongs to, as we have done here. Okay, so we will keep on continuing these steps until there is no increase in modularity value. So by the end, we will have all the communities assigned. Okay, so now one very important difference that is there between fast algorithm and the next algorithm that we are going to study, that is Lovain algorithm, is that here initially we are starting with all the nodes and there are no edges. Okay, so you can see that there are these nodes and there are no edges, and we are calculating the modularity value based on this network structure. Okay, and then on one by one step, we keep on adding the nodes and we keep on adding the nodes till the modularity value starts decreasing. Okay, so yeah, so this is how the fast greedy algorithm works. Anyone has any doubt? Is it clear? Is the explanation clear? So do you get the intuition behind fast greedy algorithm? Okay, so now we will move on to our next algorithm. Next algorithm is Lovain method. Okay, so the Lovain method, it constitutes of two main steps. One is modularity maximization, another is community aggregation. Okay, and Lovain algorithm can be used to identify hierarchical communities. Now we will try to see that how Lovain method can help us to identify the hierarchical communities. Okay, so now I have told you that this particular algorithm, it constitutes of these two steps: modularity optimization, and the other is community detection. So let us discuss how this works. Okay, so in this algorithm, first we will start with this network. Okay, so the network has all the edges. Okay, unlike the previous algorithm, we have considered only nodes and no edges. Okay, so this node, when it start, it will have all the edges and all the nodes, and all the nodes, as it was in the greedy algorithm, will be assigned to different communities. Okay, so all these nodes will be will be assigned to different communities. You can see that there are 13 nodes. Oh, sorry, not 13 nodes. I think there are 16 nodes. Yeah. So in this network, there are 16 nodes. So there will be 16 different communities. Okay. So initially, when we start, there are 16 communities. Now, again, as we have done before, we will start with a seed node. So suppose let us assume that this is a node that is a seed node initially, and then I will try to assign like another node to this community. Okay, till the time, and I will identify the node by adding which the modularity is maximum. Okay, so I will look that which node should be added. Suppose this node is added. Okay, then next step, maybe this node is added. Maybe this, again, this node is added. Then this node is added. And when I add this node, after beyond that, there is no increment in the modularity value. So what will happen is, at that point, we have to freeze this community, and then we have to check another seed. So maybe then I started with this seed. Okay, so if I start with this seed, these all belong to now one community. And then maybe these belong to one community, these belong to one community. Okay, so we will keep on checking the modularity value as we have done before, and we will keep on adding the nodes till the time there is no further increment in the modularity value. And this is how we can identify the communities in the network. So this particular step where we try to maximize the modularity value is called as modularity optimization step. Okay, so now, for example, you have this particular network. Okay, and you have these few communities here. I can see a community here, then there, this is second community, this is third community, this is fourth community. Okay, so now next comes the community aggregation step. So in community aggregation, what we do, we represent each community by using a single node. Okay, so here each community will be represented by a single node, and number of inter-community connections. So number of connections that are there within the community. Okay, so for example, if I am considering this community, then this, then we have this edge, this edge, this edge, this edge, and even this edge. Okay, so these all are inter-community connections. Okay, so we will consider all the inter-community connections, and those inter-community connections will form a loop. Okay, and like summation of all the degrees will form a loop, and all the all the intra-community edges will form a loop, and all the inter-community edges means number of edges from this community to this community will form an edge in between these two community nodes. Okay, so now this is a new network. Okay, so now we will again apply the modularity optimization on this network again. Okay, so when you apply modularity optimization method on this particular network, you will again identify the communities. So maybe these both fall into one community and these both fall into another community. So then again, you will aggregate. In this way, like you will keep on repeating these passes till the time there is an increment in the modularity. When the modularity starts decreasing, you will stop at that particular step. Okay, so now when you have the communities, the nodes, again, you can unfold these communities and you can identify the hierarchical structure in the communities. Okay, so now Lovain community detection algorithm, it not only helps one to identify the disjoint communities, but it also helps you to identify the hierarchical structures in the communities. Okay, so this is the overview of the community detection algorithms by using modularity method. Okay, so now next we will discuss the limitations of these two methods. Okay, so first limitation is the resolution limit. Okay, so what does this limitation says? This limitation says that whenever we are using modularity maximization, okay, so whenever you are using modularity maximization, maybe in greedy method or in Lowen method, as we have seen before. So whenever you are using modularity, you will get large communities. Okay, so for example, a very simple example is of maybe suppose you have these clicks. Okay, so let us assume I have clicks of size 4 each. Okay, and these clicks are again connected. So whenever you are using these type of methods like modularity maximization, it will identify this entire structure into one community. Okay, but ideally what should happen is like all these should be separate communities. This should be a separate community, this should be a separate community, this should be a separate community. So the modularity maximization method has this limitation that it combines the smaller community into bigger communities. So it's really difficult. So if your application requires you to identify smaller community, then this particular algorithm is not going to help you. Okay, so next is degeneracy of the solution. So what is this limitation? So suppose you have modularity value maybe zero point 0.8. Okay, so there will be a lot of different combination of communities that you can get with the modularity 8. Okay, so ideally like this should happen that for a particular value you should get a particular type of particular structure, particular specific structure of communities. But that is not true. It largely depends on what seeds you are selecting and like what seeds you are selecting. So basically for one modularity value, there can be many combination of different communities. So when you run this algorithm again and again, it might give you different solution each time. So this particular algorithm, it does not give you same communities each time it runs. Okay, so if you are running with different seeds, it will give you different communities. So yeah, so these were the limitations of these two algorithms. So up till now, we have almost completed the identification of disjoint communities and hierarchical communities. So in the next lecture, I might cover very few algorithms in order to give you intuition about overlapping communities. So in the next lecture, we will try to identify how to compute the overlapping communities, and the overlapping communities are real world scenarios. So generally, whatever communities you see in the real world are overlapping. But computing the overlapping communities is a really tough problem. So it's not a very straightforward problem. So here also you can see that whatever algorithms we have seen, they are not that straightforward, right? So imagine that you have to compute the communities that are overlapping. So the complexity of the problem increase. So in the next lecture, I will try to cover few algorithms that will tell you that how to identify the overlapping communities. And for those people who are interested, you can read this paper. So this is just a second. Okay, so you can go through this paper if you are interested. So this paper has huge number of citation and it is a very popular paper in community detection field. So yeah. So with that, we are done with today's portion. So we are almost done with community detection algorithm. I might cover like half of the next lecture. I might cover another community detection for overlapping communities. And then we will start with the application. So we have seen that community detection has different application, starting from recommendation systems to fake news detection to information diffusion to evolution of the networks. So all those different applications we are going to see from now onwards. So yeah, today we have winded up early. So yeah, with that, we will end today's lecture. So any doubt, anyone want to ask anything?
So, ma'am, for this modularity maximization, do we have
Mhm.
numerical as well,
Do we have?
or numerical or any problem solving for this?
Okay, I'll try to identify and I'll post. I'll post a few questions on this particular topic.
Okay.
So otherwise, what you can do is you can try looking into these example, like how do we calculate this? Okay, how this community aggregation is calculated, how this modularity optimization is calculated. So I'll post a link if I find out something. Otherwise, you can check it in detail that how like these are calculated, these different steps.
Okay.
Ma'am, although this modularity concept which you had told, that is mathematically it is clear, but actually intuitively I'm not able to understand that the difference and the more the difference, more well connected the community is. If you can just give an example, because I was just thinking that if, like say, in a normal two regular graph, if random graph is able to generate the same kind of connections, so the difference will become equal to zero. And the moment it is zero, so random graph have actually captured the complete community. So how it is that if difference is zero, then community structures are not there, and if difference is zero, then community structures are there. So, intuition wise, mathematically yes, we had seen, but if you can give some example, intuitively we can just find out that difference is
Okay.
actually making.
Okay, I think in the starting of the lecture, you only answered that random network may we do not have power law distribution. Power law
Yes, uniform.
distribution is in the social networks,
So,
and in these networks we have more uniform degree distribution, right?
yes, ma'am.
Up till now, is it clear? अब देखो कि जो
Yes, ma'am.
सोशल नेटवर्क है, ठीक है, सोशल नेटवर्क में नेचुरली देयर विल बी ग्रुपिंग, ठीक है, नेचुरली क्या होगा
Yes,
कि जो ग्रुप है उसमें इंटरकनेक्शन ज्यादा होंगे,
yes, ma'am.
like okay, for example, we are the students from social media analytics class, so we all will be more connected from maybe some other students from some other class, ठीक है, तो सोशल नेटवर्क्स में ये प्रेफरेंशियल अटैचमेंट होता है, ठीक है, naturally this preferential attachment is there. So naturally the nodes that belong to one group they will be more connected, there will be more connections within than the connection to the outside groups.
Yes, ma'am.
Okay, but this type of thing is not there in random graph. Random graph में क्या होगा कि generally like in a particular group, if we are considering like for example ABCD is a group, so like there will not be more interconnection within that group as compared to the connection outside that group.
So
So I
where,
hope I am able to give the intuition. तो अब क्या
uh,
होगा कि इधर interconnection ज्यादा है, इधर like हैं connections but maybe मतलब like they are a little bit uniform. तो अब जो difference होगा वो there will be some difference. Okay, so if grouping is there, there will be more difference. If like the grouping is more dense, then there will be the difference will increase. So am I
so
able
ma'am,
to give
random
the
graph,
in? Mhm.
your explanation I have understood is that random graph we are generating on the complete vertex set and then comparing it with the subgroup that community which we had detected in that thing. So,
No, random graph में हमने वो preserve किया था, if you remember, degree
uh,
distribution.
yes, ma'am. But we are generating random graph on complete vertex set. We are not
Hmm.
generating on
Hmm.
sub vertex.
Right, right, right.
Okay, okay. Then difference will increase. Yes.
Yes.
Okay, ma'am. Thank you, ma'am.
Yeah. Okay. Anything else? Anyone? Okay, so with that, I'll wind up this lecture today and I will try to post a few more questions so that this concept is even more clear. You can try programming low-gain algorithm. Okay, so you can try taking a network and then applying the low-gain algorithm in Python and also maybe it will give you more intuition of like how these algorithms are actually used when you are going to implement the other applications that we will be studying in our further lectures. Okay, so try like in the Python, we already have the libraries which tell you, which gives you the functions like Grivan, the a bit Grivan algorithm, the algorithm that we have covered in last class, then Lowain algorithm. So you can try small snippets of code and you can implement the community detection algorithm in Python using NetworkX library. So yeah, that thing you can do as an homework. So then like from the next lecture, we will try to cover as many applications of these community detection as possible. So yeah, with that, we'll end today's lecture. So thank you everyone and happy Sakrant everyone.
Thank you, ma'am. Same to you.
Thank you, ma'am.
Yeah.
Thank you.